Hello, everyone. I would like to welcome you to this recorded virtual lunch and learn in our continued series as we upload these to YouTube. This pre recorded presentation was delivered by Jeff Wellen from Amtrol and discusses water hammer in domestic and HVAC applications. Jeff has over 55 years of experience in plumbing and heating and has held various roles at Amtrol. Jeff has been a production supervisor. He has worked in the engineering, quality verification, and has been an associate trainer as well as worked in the technical service side. For the past several years, Jeff has taken the role of senior technical service representative of the Amtrol Technical Support Department, where he is focusing on product training and education. Jeff has trained thousands of employees, professional contractors, wholesalers, engineers, inspectors, and sales representatives in this role and has been instrumental in expanding Amtrol's product education efforts. We joined this training slightly after Jeff has started his introductions.
Uh, the next page here, here's the different hammer arrestor designs that I could dig up. If you look at the very first one on your left, the piston design, this particular model does not have an air charge fitting on it. There are some models out there that do have an air charge fixture on it. They're effective models to use, especially under the sink, or if space is, if space is limited, then sometimes you have to go with those. The middle one, that's a diaphragm design. And what we're kind of showing there with the white arrows, that's the pre-charge in the tank. And that red arrow in the blue, that's the hammer coming into the tank and being absorbed by the diaphragm. And then last but not least, we have the bladder design. And again, I had to enlarge that. Some of these tanks are quite large, but I had to enlarge that so that you could see the air pressures now surrounding the bladder itself, and the hammer or shock that's coming into the tank is on the bottom there, and you can see the red arrow. The advantage to a bladder design, in bigger applications, is a bladder is probably your best way of absorbing shock. Reason being a lot more surface area on the bladder, as you can see, compared to a diaphragm style, and or of course the piston style. So there's more advantages to a bladder design. Now, what is hammer? I hear all kinds of things. What's hammer? Water hammer is the term used to define the destructive forces, the pounding noise, the vibration, the thump, which develop in a piping system when a column of non-compressible liquid flowing through a pipeline is stopped abruptly. The tremendous forces at the point of stoppage can be, in effect, to that of an explosion. And, in some of the commercial applications, if you don't stop the hammer, you see pressures up to 4,500, 5,000 pounds just from a hammer. All righty, what are some of the common causes of water hammer? Well, quick acting solenoids on flush valves, dishwasher, washing machines, ice machines, and commercial washdown hoses, booster pump startups, fire pump startups. And again, booster pumps and fire pump are usually larger systems, but I have seen them in a residential application. If anybody has any questions, feel free to stop me at each and every point.
The only thing that's come through so far, Jeff, is someone was wondering about the water hammer reference with the baffle design, and I'm assuming he's talking that may be the air chamber style instead of having a piston.
Yes, that's really old fashioned. I couldn't find anybody that still makes those. I remember back in the day, my uncle used to make them, and he'd just make the pipe longer. He put in a 4 or 5 foot pipe and cap it off at the top and then add water. But the problem with that design is sooner or later, that air charge, whether it be atmospheric, gets absorbed by the water. And then you have to go through the same experience. You got to drain that pipe down and then fill it back up to get a atmospheric charge in it. Does that answer that question? Okay. Okay. So, what's the big deal about controlling water hammer? Well, some of the things that may happen is fixtures start running, wasting water, especially in toilets. Toilets do not like any water hammer. Pipes may leak, causing water damage. If they burst, it's going to be damaged in the building. Damage to check valves, especially pressure regulators and water heaters, water meters, excuse me. They do not like that. And pipes may burst, causing water damage, or worst case scenario, water fire sprinkler system, life-saving water may not reach the intended affected area. So that's a really big deal, because when the sprinkler goes off, there is a fire. And if there's a fire, people want to be protected so they can get out of the building.
Jeff, I did have one person ask if it is possible to have water hammer when you do not have flowing water.
I haven't seen any cases of that. Usually, the only case I've ever seen of that is when there was a backflow preventer, a dual check backflow preventer. And what happens is the pressure may drop on the backside, say the town or whoever's supplying water, the pressure may drop on the backside of that pressure reducing valve. And what happens, it actually makes those uh, stop devices or flappers, they may start to vibrate because of the pressure differential inside the pressure regulator. And if that happens, that chattering noise, it may sound like water hammer, but that it'll travel through the pipes. And if it's in a residence, which the one I ran into was, it travels through the pipes. And of course, it's only going to start after midnight when people are starting to go to bed. So that's usually what it is. It's some device in the line, whether it be a pressure reducing valve, water heaters, water meters that have diaphragms in them, that can cause thumping in the pipes, confused with water hammer. But anytime anybody hears thumping in the pipes for whatever reason, we all rush to the water hammer answer is water hammer, but there are some other causes. Any other questions?
Another one I have is, can water hammer occur at the start and the stop flow, or just when the flow is stopped?
It can actually occur at start, which is quite interesting. When you have for example, a good example is a sprinkler system. I know in Colorado and a few other states, any house over 5,000 square feet is required to have a sprinkler system. And during the testing, when that pump starts up, it's going to be more gallons per minute and more pressure all of a sudden, because when those fire pumps start, they start with a bang. So your standard flow could be 200 gallons a minute, just for example. but then you go from 200 to 1500 gallons a minute in a split second, and you start getting surge water hammer, and that will travel down the pipes right to the sprinkler head. So it's got to be controlled, otherwise it's been known to blow out sprinkler heads. And of course, once you do that, you make the system unusable.
And then here's one to test your code knowledge. Someone wondered if water hammer arrestors are required per NFPA 13.
Yes.
There you go.
Yeah, they're called NFPA 13, I believe refers to them as surge, whether it be pump startup or pump shutdown. They call them surge tanks in NFPA.
That's all I got so far.
Okay. Good questions. Alrighty. Here's a graphic depiction of what's happening. It's not showing pump startup or shut down, but just in a regular residence. You know, so the valve is closed, we open up the valve, we start getting a flow of water through the pipe, and then we slam that thing shut, whether a faucet or a lever of some sort or a solenoid. And that jagged line is actually a depiction of the shock as the valve closes suddenly. So the way I describe it to most plumbers, if they ask what is water hammer, I say, think of this, you're running at full speed and somebody slams a door on you. You hit the door, you don't go forward, you go backwards with more force than you were going to start off with. So they kind of get the picture that way. It's very depictive. I've never demonstrated that. I don't think I ever will. Number one, I can't run that fast. And number two, I'm always looking out for slamming doors. But this picture gives you a good idea what's going on in the system at the time without a device to control the water hammer and with a device to control the water hammer. All righty. Now, the next couple of sizes, any questions on that last section? No? Okay. All righty. Here's what we did. Amtrol has our own sizing, which is really taken from the PDI book. And these are the things you need to know. You need to know pipe size, effective pipe length, how long is the pipe, what's the maximum flow, static pressure, and flow pressure, maximum shock pressure. What is, so what is maximum shock pressure? Well, that's the maximum that you want to have the system see. So for example, say I only wanted the system to see no more than 100 PSI, then that's what you would put in there. Fire systems, you don't want to see, especially for sprinkler heads, you don't want to see any more than 175 PSI. So you've really got to look at the components downstream. What is their max pressure rating? And you want to be under that, of course. Flush valves, especially, they don't like to see, 100, 120 pounds. So always get that specification. That's really important. So the selection of the water hammer arrestor, you got to determine system velocity, determine kinetic energy, calculate total kinetic energy, pressure factor, acceptance factor, that gives you the total volume of the tank, and acceptance factor. And the reason why that acceptance factor is in there, acceptance volume, most devices have a maximum amount of water they will accept, And you want to pay attention to that because it may say total volume is 10 gallons. That's fine. And I need a 10-gallon tank. But my acceptance volume may be at that point 90%. So if it's 90%, that means 9 gallons of water in a 10-gallon tank. There's no room for air pressure in there. So those are some of the things you got to pay particular interest in. We're going to go through how to fill it out. So don't think we're going to leave you stranded with just the formulas and walk away. So next page.
Jeff, just jump in while they're up fresh. I have two questions for you. One person just quickly asked, could air in the water system actually create water hammer?
Yes.
Okay. And then another one is, he was very specific about the fixtures, but basically he wants to know if you don't have the static and flow pressures, can you still size the hammer arrestors?
Not very well, because you're guessing. I've been doing this for a long time, and every time I assume something, you know what it does to you. So you really need static and flow pressure. Though those are really important, especially static. That can make or break you. So, for example, I got a sprinkler system. I keep going back to that because that's probably the easiest thing. I got a sprinkler system. Max pressure on the system is 175. But if I got 170 coming into the system, we're only talking 5 pounds, and that's going to be an extra large tank. So to keep it under, if you put a flow restrictor in there of some sort to reduce that flow and reduce the pressure or pressure reducing valve and maintain your flow, that would be the way to go. But as we go through the sizing, it's going to become almost self-explanatory. So any other questions on that?
Oh, so he's wondering, like, if you're going into a retrofit where you don't know that information, how would you go around sizing it on like a retrofit where you don't actually have that available to you? But I'm thinking that we'll probably discuss that a little bit more when we go through the sizing.
Yes. What I've done in the past when I was out in the field, and I've been out in the field quite a bit, is I just put a pressure gauge on an outlet somewhere, start the flow, and just read the flow pressure off of that. So it will drop, and that's going to get you close enough without having to meter it or anything else along those lines. But we can get into that more at the end if you wish, and that's fine. Okay, so we're starting our sizing. So pipe size, in this case, we're going to use 6-inch. I'm using larger pipe sizes because it just gives us a little clearer picture. Of course, there are smaller pipes. I know there's 1/2 inch. I know there's 3/4 inch, 1 inch, but I just use 6 as an example. So we got a 6-inch pipe. Effective pipe length, in this case, 5,000 feet. Maximum flow is 200 gallons per minute. Static pressure when nothing's flowing is 90 PSI. Flow pressure is 80 PSI, so it didn't drop much. Maximum shock pressure, and PDI recommends no more than 150 PSI, and that's for residential. Commercial, as we know, can get much higher, but for residential, 150 PSIG is what they recommend. Now, we have that information, so now selection of hammer arrestor, determine system velocity. So if you notice, we have velocity charts on the right-hand side there, and that's right out of the PDI book. So to determine system velocity, and they do it for you right here. You see the 200 6-inch pipe. You come down, and it's 2.25 feet per second, and that's the flow. Determine kinetic energy, and kinetic energy is about 1.1. We did take some liberties when we were developing this, so it looks like 1.1 to us here. And then calculate total kinetic energy, and that's 5,500 foot-pounds per 1 inch of 1 inch of foot of pipe. So that's our total kinetic energy is 550. So now with that information, we come up with pressure factor, and that's from the chart table A. And 550 pressure factor is 1,760. And again, this is for residential. I don't know any residents that have 6-inch pipe, but it's for residential. Then your acceptance factor is 0.10. And that comes from, again, we supply the chart. That comes from the chart over here. You see 80. That's the flow pressure, and that's why the flow pressure is so important. And 90 is our static, because without the flow pressure, we wouldn't be able to determine that. Now, we used, for a bigger tank, if you notice, it says model number D7, that's a 53-gallon tank. But so we take the minimum volume, total minimum volume, and the formula is right next to that. And we come up with 23.4 gallon tank. And the acceptance has to be 2.34 gallons. And again, remember, in most, if not all, hammer arrestors, most of that tank is going to be air pressure, and the volume of the tank is going to be filled with air. That's what relieves the hammer. But if you look over here, it says the D series models, a D7, smallest tank's 53 gallons. And I've been asked, is it okay to oversize? Especially on water hammer, it's okay to oversize. If you can, I always do it, and it saves you problems later on down the line. And acceptance volume, 2.3 gallons. So on this 53-gallon tank, the maximum acceptance is 65%. So you're well within the acceptance volume, and you're well within the total volume of the tank. Okay, I know that's an awful lot of information to be throwing at you. This is something you might have to digest or try yourself a couple of times and see how that works out for you. And if you have any questions, feel free to filter them through Brian, and Brian will send them to me, and I will get back to you. How does that work for everybody? Good? Okay. Make a good tank.
I do have one question that came in, and it's why couldn't you use a much smaller water hammer or arrestor like a piston? For the example, I mean, Jeff used a 6-inch pipe, so you're going to end up with a big tank to begin with, and it looks like we're kind of, in a big flow situation. There are instances where a piston style or even like a diatrol, the mini diatrol, would be big enough and would fall under the classifications of PDI through that, A through double F standard.
Yes.
He's just giving you an example that has big enough numbers so you can actually see what's going on. The volumes tend to get kind of small when you're looking at the smaller arrestors, but please.
Yeah, because I've run into some arrestors I've sized and it's 0.015. And that was, the acceptance volume I needed. So you come out with, 9/10 of a gallon, the size of the tank. So it's, yes, the answer to your question, yeah, you will run into much smaller. But even on the smaller tanks, this formula works very, very well. No other questions?
Nope, that's all I have so far.
Okay, so just like in real estate, location is key. Ideally, you want to locate the tank as close as possible to the offending fixture. And on a single source fixture, such as a dishwasher or washing machine, it is much simpler. On a multi-fixture, it is more complicated, such as multiple flush valves in a building. You could have a bank of 10 of them there. Keep in mind, and this is something to really keep in mind, that the further from the source of the hammer causing the fixture, the further the hammer will travel before being relieved. So if the tank is 20 feet away, remember that shock or hammer is going to travel those 20 feet before it gets relieved, i.e. point of relief. I believe that's what the PDI calls it. So keep that in mind. Sometimes it's near impossible to get close to it, especially if it's a fast-acting hose. And the guy's got the hose and it's 20 foot long or 30 feet long. Again, as close as you can get to it. Nobody's going to put a hammer arrestor on the end of the hose. Nobody I know of anyways. So anyways, that's just something to keep in mind. Alrighty, and here's a description of the water hammer arrestor coverage. Should not exceed a fixture branch line over 20 feet. The water hammer arrestor should be placed as close to the quick closing valve as possible for optimal performance. Again, there's times, sorry about that. There's times when that's impossible. So, keep in mind, you don't want to be too far away. I use the 20-foot rule, and that's kept me out of trouble for pretty close to 48 years anyways. Any questions on location? Again, it's just...
One quick question that came up was, I couldn't remember the acceptance factor chart that you showed. Was that specific to Amtrol, or was that like standard to any type of tank?
On most manufacturers, you will see that. They'll give you the size and they'll give you, the maximum acceptance in water or fluids. I've seen it on a couple of our competitors have that on their charts. I don't want to mention names, but there's quite a few different styles and designs of these tanks. And I've looked at theirs and they may not call it maximum acceptance. They may have another term for it, either acceptance or maximum volume or some other words like that. But yes, most manufacturers have them to answer your question. Yeah.
Sorry, so it would be specific to the manufacturer. It isn't just some table that you're pulling it from.
Oh, it's to the manufacturer. Yes. Yes, correct.
And then I have another question that just came through. It says, can a water hammer arrestor be located above the ceiling? Does it require maintenance that would require it to be located lower within, access reach?
You always want to be able to get at it. That's a good question because I've had that multiple times from installers. The reason being, like everything else in the world, it doesn't last forever. You need to be able to get in there and replace it. When you install it, there may be some pressure changes you have to make to the device. Again, you want to be able to reach it. But also, can I be on a riser pipe that goes up above the ceiling tiles? Yes, you can, just to keep it out of the way, because nobody wants to look at a hammer arrestor in a men's room or anything else like that, wherever you put it, or in a house. I mean, that's not my most prized possession, a hammer arrestor. So to answer your question, yes, you can. Just make sure there's a way to get at it. All right.
That's all I have so far.
Okay. Okay, connection size tip, and I think this is something I've been working on for quite some time. And you'll want to keep the connection size as close to the pipe size as possible. For example, if the pipe size is 2-inch, the connector on the vessel you are using should be no smaller than 1-inch. And the formula below will show you why it is important. This is Bernoulli's law or principle. And the larger the difference from system pipe diameter to the connector diameter, the greater the velocity increase when entering the water hammer arrestor. This increased flow velocity can damage diaphragm style water hammer arrestors, which there's quite a few out there. And the connector of the water hammer arrestor should not be smaller than half the diameter of the system piping. I've always preached that. But here's the question. I don't want to put in a giant tank. I want to put in, let's use the 53-gallon tank. I don't want to put in a 53-gallon tank. You can use 2 smaller ones and manifold those together, excuse me, to get your pipe size. So there are ways around it. Now in the principle, we kind of filled it in. Situation 1, system velocity is 2.25 feet per second. System pipe diameter is 1 inch. Connector diameter is 3/4 inch. So if you look at the formula, I'm not going to go through how to use the formula, but if you look at that, that equals 4 feet per second, which you want to be under or at 6 feet per second as normal flow through a pipe. Excuse me. Now let's look at situation number 2. System velocity, same as before, 2.2 feet. Pipe diameter is 2 inch, a little bigger pipe. Connector diameter is 3/4 inch. We're using the same hammer arrestor. But look what it does to our velocity. It went from 4 feet to 16 feet per second. That's quite a difference. So let's think about that. This water is now flowing through that connector. It's hitting the diaphragm. In a good situation, in situation 1, it hits the diaphragm about 4 feet per second. Situation number 2, it's hitting the diaphragm about 16 feet per second. It's almost coming out like a knife. And that will cause a lot of wear and tear on your device, whether it be piston style, whether it be diaphragm style, bladder style, and even if you just had a capped off pipe, there is erosion that's going to happen, and you'll be replacing that unit more often than you want to. So this is a good point to keep in mind.
Since you brought that up, Jeff, there is a question on here about, in your experience, what's the different life expectancies for like a piston versus a diaphragm water hammer arrestor in like a heavy use application, like a public restroom?
Piston style, if you notice, there's 2 rubber O-rings on that piston, and of course that's going up and down. And in a public restroom, I would imagine it gets used an awful lot more than a residential. So with all that said, you'd probably get, I don't know what the longevity is on those, but you're probably looking at anywhere between 1 and 5 years, again, depending on usage. I have seen just the opposite of that in a residence. I had to go to one in a town near us and advise the guy on what to change it to. And that particular piston style was in there 25 years and worked flawlessly for 25 years. Diaphragm style, remember, every time that diaphragm goes up and down, depending on velocity and stress and strain, you're probably going to get anywhere between 5 and 10 years out of that, 10 being a stretch. The bladder style, you're going to get a lot more longevity because even with an increased velocity, even with this case, increased velocity, remember that's going up in between the diaphragm bladder, and that bladder, because the air is surrounding the bladder, is more capable of absorbing that. So with all that said, what would you expect for a life on that? I had a guy at the airport just change his, and his were 10 years old. So again, heavy usage, but they were 10 years old. So on the bladder, you'd probably get 10 to 15 on the outside. Does that answer the question?
Yep. Yeah, that was those. And then last one I have right now is, do you recommend putting a hammer arrestor near check valves?
Yes. Yes, I do, but I don't want it right on top of the check valve. Yeah, I do, because when you run into, when somebody shuts a faucet, it's going to go back to that check valve. You want to be within a foot of that check valve in a residence. But yeah.
And just making sure, are we talking before or after the check valve? So
after the check valve.
After the check valve, okay.
Yeah, you never want to put it before because that's too late. The check valve is going to close and the water hammer arrestor is going to be isolated. So you always want it after the check valve. The other thing too, if you actually put the tank before the check valve, you can get that chattering I was talking about, because now you're going to have 2 dissimilar pressures, and the check valve is going to open, close very rapidly, and it's going to chatter, or you may have that thump that my wife used to complain about all the time. So yes, always after. All righty. Any other questions on that?
No, not as right now.
Okay. All right. So I think we've kind of talked about that. The effects of increase in velocity may reduce the effectiveness of the device to control the water hammer, because all that shock and water is trying to enter that connection point. And if we reduce that, you may not be as effective as to control the water hammer. So just a point to keep in mind. All righty. Any questions? Any other questions? I'm sorry.
Oh, sorry. No other questions. I keep forgetting to unmute myself. One other thing I would talk about is like I had an example, the point of relief, because PDI talks about it and they call it the point of relief. I know you talked about it a little bit. What happens in a system where, because PDI refers to the point of relief as the location where the pipe size goes up. I believe it says 2 pipe sizes. What's your feeling in a system where you don't have that type of increase in pipe size? You know what I mean? Like you don't really get 2 pipe size increase. Do you just go to the next increase and that's your point of relief? Or do you have to go all the way back to like where the water's being supplied to the building? Well, I think this comes into when you're determining the effective length that you're trying to calculate.
Yes. To answer your question, yes, that comes into your effective length that you're trying to calculate. That actual, when you go from 1 pipe size, let's say 1 inch, and I'm going to go up 2 pipe sizes, so I'm going to be 2 inch or 3 inch. What that does is it gives the hammer or shock room to spread out, and that reduces the shock. So to answer your question, that is another point of relief. I kind of taken them to task a couple of times on that and haven't won yet, but sooner or later I will. I always consider point of relief where the shock is going to end. Whether you increase pipe size or whether you put in a device to just prevent it from going any further.
So like a check valve, once it meets the check valve,
right,
go any further. So that's going to be your point.
Exactly.
I do have someone that brought in a question. I can actually respond to this one, make myself, feel good. So they were asking about maintenance, on the different styles. So I know the piston one, like especially the piston style that you showed at the very beginning, those are a maintenance device. They fail and you have to replace them. There's nothing that you really can check on them. Unless they're the updated version that you were talking about that has the ability to have an air chamber on the top that you can recharge. So you could technically test that after removing it from the system and see if they're still, if it's waterlogged or if there's, still charged in the pressure. When we start talking about the other styles, the bladder and the diaphragm, those are just going to be like an expansion tank. They're just like a, does the Minitrol have a Schrader valve on it? I think.
No, that's been taken off. It just has a pre-charge of 22 psi.
Yeah.
That's
so yeah, the residential one. So the smaller one, most of the bigger diaphragm tanks will have a Schrader valve that you can reach, test the charge and see where it's charged at. One thing people forget about these tanks is when you're verifying the pre-charge on these, you want to do it when there's no water in them, because once you pressurize the tank with water, it's not an accurate reading anymore.
True.
Yeah, that happens way more in boosters, and that's a different topic. But another thing, knowing that they failed is you're going to get water hammer. I mean, that's the one thing that kind of sucks about that. It's not like it's going to slowly, it may slowly fail on like a piston if that air charge is being lost, but on like a diaphragm tank, as soon as that bladder or where the diaphragm ruptures, it has failed. So it just gets full of water, and you would know that with the bigger ones because you can just test it by tapping the Schrader valve, and if water comes out, then obviously the seal has failed. Any other input you have on that one, Jeff?
One of the things to think about, with the piston, remember, there's two O-rings that are riding along the walls of that cylinder. We used to make those way back in the day. I'll probably go back 35 years ago. And in fact, I remember making those. Again, they're pretty sturdy little characters, but there's nothing, absolutely nothing you can do to maintain them other than the air charge. And that goes for also the diaphragm style. There's nothing really you can do to it other than checking the air, occasionally. You could make it part of somebody's PM. Also, on the bladder style, the nice thing about most bladder tanks is you can replace the bladder. So like you said, if you had a failure and you got water shooting out of the air stem, the bladder is dead and can't be reused and not functioning the way it should. The good thing about it is you can replace the bladder and start from scratch versus replacing the whole tank. So that the bladder tanks are more maintenance orientated versus a diaphragm piston style or just air over water. So diaphragm piston style, air over water, those are just got to be taken out, thrown away, start all over again.
Jeff, can you go back slides to the point where you had the 20-foot and it showed multiple hammer arrestors?
Yep.
So yeah, this one right here. I think we talked about it, but this is directly from the PDI, and this is really like a bank of urinals, I think is what they're trying to show on this example. And one thing, I think we kind of said it, but we said it really quick, is you can see that they have multiple hammer arrestors. So you can split the load among multiple hammer arrestors instead of just using a single hammer arrestor, as long as your actual volume is correct, right?
Correct. And even if you're a little oversized, that's fine.
And on that note about oversize, is there actually any harm in oversizing a hammer arrestor compared to undersizing it?
Never. Like I said, I used to be in the business. We oversized everything, and we never got a call back. So oversizing saves you money in the long run because nobody wants that phone call.
And then I'm just taking a quick gander over the PDI thing because I don't think they bring up anything that's much different than what we've talked about. Nope. Because this is what everyone's gonna kind of, and if you guys don't have this as a reference for some reason, we keep saying PDI, it's PDI WH201 is a standard, and I'll make sure that you guys all get a copy of it. I'll send it out to you just so you have it. And it goes, they do it slightly different. On theirs where they have like the AA to an F, and they do it off of fixture units. Do you see any problem with the way that they do that instead of trying to do the actual math and see what the volume should really be?
Because I'm old and I can still function, I like doing the actual math. It tells me exactly where I am. If you're just using that A through F sizing, I mean, there's nothing wrong with it. But, you know, if I'm at F, how close am I to, you know, to being undersized?
Yeah, I
And
hear you.
that type of stuff always makes me leery because I have no idea where I am. It doesn't tell me, hey, you know, I need a 10-gallon tank. Well, I need a 10-gallon tank. It doesn't tell me that. So doing it by fixture, you may come up with like 9.5 gallons. You know, it close enough, and shock is not good enough. I just made that up. It's pretty good. But that'll always get you in trouble. I found just from experience, so I'm just speaking from experience only, but that is, I like to know exactly where I am in the scale. You can use the PDI one. I mean, that's fine, and that's been successful for years and years and years. So I can't throw a rock at it, but I always like to know exactly where I am. You know, am I that close, or do I have a mile? You know, and it's probably because I'm so nosy.
So the last thing I'll chime into is talking about that PDI is because, you know, I've read through it, and the PDI is very simple system oriented. It is almost how I want to put it. So
Yeah.
it's really hard to extrapolate it into larger systems. We had people that were talking, that's where the example came up of, hey, you know, I am not going to have, you know, they have a bad example probably, but a 2-inch line going to the bank of bathroom fixtures, and then all of a sudden they only go up to a 2.5 or a 3-inch size. So according to PDI, they haven't hit the point of relief. But if anywhere in that system, they don't even mention the fact, hey, if you have a check valve, that's really where this zone stops. So you're just arresting it to that. So I think
Right.
seeing the math and doing the math at least a couple times on your own to understand exactly where those numbers come from is always beneficial.
Yeah, one of the things, if you do the formula, I've probably done it 10,000 times if I haven't done it once. But once you do it, it gives you intuition. So you may walk into an existing job site and somebody says, hey, you know, I've always had a little bit of water hammer. And you look at the connector and you look at the size of the tank, and because you've done the formula and it's kind of in the back of your head, it gives you the intuition saying, hey, wait a minute, this thing's not too small, but you're right on the cusp. If you went up a size and up a size on the connector, you'd probably be okay. So yeah, I think it's always better to have that knowledge than to not have it and just depend on a chart.
I don't have any other questions. If you guys do have other questions, please put them in. We are getting close to the end of our hour. So if you guys have more questions, please keep them coming in. We can keep answering them, but I seem to be kind of putting in my own 2 cents to fill out a little bit of the time. But I would like to thank Jeff for coming in for us and giving us the presentation. And of course, I'd like to thank all of you guys for spending your very important lunch hour with us. I hope you guys got out of it what you were hoping to. If you have any questions, you guys should all have email contacts or contact information for me, Brian, directly. So you can always send questions directly to me. If I don't know the answers, as you can see, I definitely have people I can reach out to make sure I get the answers for you. But that is all I have. Do you have anything else you want to put in, Jeff?
Nope. The one thing I'd like to put in is everybody please stay safe. We appreciate your business as always. And we're here. Brian and I are here to help you with any problems you may run into in the future. So thank you for attending.
Yeah, and the last thing I'll put out is because you guys know that we've been putting these on for a while. You probably won't see another one until at least the new year just because of the holidays. So I'll reach out to everyone again if we have another seminar going on, just so you guys can all be part of it. But thank you guys again for coming, and that's all we had. So you guys enjoy your afternoon. Thank you.
All righty.